Hello and welcome to Big Day in Education. I'm Ryan Baker. Today we're going to talk about the Q matrix. What is the Q matrix? It has nothing to do with Keanu Reeves. It's a table where each row is an item and each column is a skill. People also call this by other names, including a KC, knowledge component model, or a skill item mapping. So if we look at an example of a Q matrix, and you see one here, you got a set of items, you got a set of skills, and you can see that item 1 involves skill 1. Item 2 involves skill 1 and skill 2. Item 3 involves skill 1 and skill 3, and so on. Every item involves at least one skill. If an item didn't involve any skills, then we'd need to create a new skill for that. So let's take an example. Let's say that these are your items and these are your skills. So 7 plus 3 plus 2 involves addition, but not subtraction, multiplication, or division. 7 plus 3 minus 2 involves addition and subtraction. 7 plus 3 times 2 involves addition and multiplication. And you could say there are other skills involved here too, like order of operation, but that's not in this set. How do we get this skill item mapping? Well, there's 3 things people do to get to it. They do automatic model discovery, hand development and refinement, and hybrid approaches. We'll talk about automatic model discovery and hand development and refinement today. We'll talk about hybrid approaches in the next lecture. So automatic model discovery. What you do there is you learn the mapping between items and skills solely from data.
So the initial way that people did this was a hill climbing based method that came from Barnes et al. But more common lately is the use of non-negative matrix factorization, which is mathematically intense and we won't go into the details. It's worth noting, by the way, that you can actually combine these two. And Pacones et al. Do a nice example of combining non-negative matrix factorization with hill climbing. So the first question in doing this is, how many skills should we use? And this is determined empirically. First we try one skill. Then we try one more skill than the previous model. 2, 3, 4, 5, so on. And we look every time we add a new skill, does the new model fit the data better than the previous model? And if so, we go to step 2. And if not, we quit and we use our best so far. But you might ask, how do we know if one Q matrix is better than another? There's several ways to look at it.
The definition that Barnes and colleagues use is that a better model has the property that if a student knows skill X and item 1 and item 2 both involve skill X, then a student who gets item 1 right is going to be more likely to get item 2 right. And if a student gets item 1 wrong, they'll get item 2 wrong. And if they get item 2 right, they'll get item 1 right. And if they get item 2 wrong, they'll get item 1 wrong. So in other words, performance on 2 items that involve the same skill should be connected. To put it another way, given a skill item mapping, you can predict for each combination of skills whether a student should get each item correct or not. And a model's degree of error is based on how many item student pairs the prediction gets wrong.
However, you're typically going to get better fit from having more possible skills. So what you can do going forward from there, as Effenberger and Pelinek and their colleagues point out, is you can compare models with different numbers of skills using BIC or AIC or cross-validation.
So there's a subtlety. Is the skill conjunctive, as in Barnes, which means if an item has multiple skills, you need every relevant skill to get an item right. If an item involves skills 1, 2, and 3, you need to have 1, 2, and 3 or you're going to get it wrong. Or is skill compensatory, as Zach Pardos proposes, where having any relevant skill leads to getting an item right. In other words, if you have skill 1 or 2 or 3, any one of them, you're going to get the item right.
So one thing that's worth worrying about, by the way, is that Barnes' approach and non-negative matrix factorization, and let's be frank, most approaches to Q matrix discovery assume no learning. An alternate way to do this is to look at student improvement over time. You fit a model like PFA or BKT from week 4, and you see how well it fits the data given the skill item mapping. Now, there's probably somebody out there right now who's saying, wait, why would I use PFA or BKT when I could use DKT? DKT is better at fitting the data. The reason is because DKT family algorithms either are going to skip the step of having a skill item mapping entirely, or they're going to fit their own Q matrix or alternative to a Q matrix. So literally, you put a different Q matrix in the DKT family, you get the exact same thing back out. And this process of looking at student improvement over time in the process of validating Q matrices, you can see in various papers, such as the ones listed here.
So the second approach we're going to talk about is hand development and refinement. This is the original way that Q matrices were created, actually. A domain expert, really smart person, creates the Q matrix using knowledge engineering, which we discussed last week. So what kind of data can we use to guide refinement? I'm actually going to give some slides with permission that John Stamper gave a talk in my class on. So 3 strategies that John talked about are, first, try to smooth learning curves. This is actually a strategy that comes from Corbett and Anderson in '95. Second, look for skills with no apparent learning. And third, look for problems with unexpected error rates. There's a tool for doing this, and it's called the Pittsburgh Science Learning Center Data Shop. You can also do it in Excel, you can do it in a visualization program, but the Data Shop's got tools to help you do it. It's a great program. I love Data Shop. The learning curve shows the relationship between the student's amount of practice, the number of opportunities the students had to demonstrate or to learn a skill, and their performance. So on the x-axis, we have how many opportunities the student has to learn the rule. On the y-axis, we have the error rates. Incidentally, this classic graph comes from Corbett and Anderson '95. And you can see that the error rate goes down as the student practices more, and you kind of hope that would be what happens. Now, spikes in learning curves often imply that 2 or more skills are being treated as a single skill. So if we look at this graph, the student seems to be getting better, then they shoot up, then they come down, then they shoot up again. And actually, this graph actually is demonstrating 2 different learning curves occurring. If you look at its 2 learning curves, it looks really smooth and nice, but if you look at it like one, it's a total mess. The PSLC Data Shop makes it possible to look at learning curves for different skill models. So for example, if you treat geometry area as a single skill, the entirety of geometry area, you don't get a smooth learning curve. But if you split it into the 12 component skills, then you get a smooth learning curve shown at the bottom right. You can actually inspect curves for individual skills. Again, this is pictures from the Data Shop. Thanks again to John for providing these. And you see that many curves show a reasonable decline, that is, less errors over time. There's a little spikiness. You're going to get that if you don't have much data. But some don't, and that's actually an opportunity to improve your model. If you have a skill that's not going like this, then either you're teaching it really badly or your model's messed up. Possibly both. The second thing you can do is look for problems with unexpectedly high error rates. There's a tool in the Data Shop called the Performance Profiler, shown here, where it shows you each item's actual error rate and the predicted error rate based on the model. If you've got an item that has an error rate that's much higher than what you'd predict from the model, you know there's something wrong there, and it's something worth looking at. Maybe that problem doesn't fit the skill you think it does. So once you've built a skill item mapping, the Data Shop can actually test how good it is for you. It applies a mathematical model called LFA, which is similar to PFA, to the data, and then gives you AIC and BIC goodness measures for the different skill item mappings you might have created. So Data Shop's a useful tool for this kind of thing if you want to do hand model refinement and development. In the next lecture, I'm going to talk about knowledge structure inference, hybrid approaches, and models with prerequisites and hierarchy. So see you next time. I'm Ryan Baker. This is Big Day in Education. Thank you very much.